I'm going to be teaching this spring my most common course, which is over in Earth Sciences, but I think it's cross-listed in engineering still and in the School of Medicine, which is biomineralization, which is how organisms manipulate crystal formation. So if you're really interested in a lot of detail, that would be a course to look at. But what I want to talk about today is what a lot of people think is the only definitive way to address climate change. You guys are probably all aware that recently we've learned that some of the non-CO2 gases can be mitigated, like the HFCs and other gases, and China just agreed to join the Montreal Protocol, which is on these short-lived pollutants. And we've learned that that's going to be a huge benefit to climate change by controlling these short-lived pollutants. And you're not aware of it, but over your lifetimes, refrigerators and air conditioners have changed the types of chemicals that are used in there and getting into the atmosphere, which are very powerful greenhouse gases. And the Montreal Protocol has been one of the most successful legislations. And that's going to certainly help things out a lot, but we still lose the whole climate battle unless we do something about CO2. And the reality is that coal is going to be the principal fuel for electricity for our lifetimes. Even if we tried to go to 100% renewable as fast as we possibly could, we'd still have to burn coal for at least 50 years to get there, and that's the harsh reality of the situation. And with half of the population of India being under the age of 14, and what's happening in China and coal reserves, for our lifetime, coal will be the main thing powering electric cars. And unless we address those sorts of emissions in a real definitive way, we lose. We exceed the 2 degrees and other things begin to happen. So the one single most important thing, if we're really serious about doing something about climate change, is to mitigate CO2 emissions primarily from electrical power generation. And so I'm going to talk a little bit about how nature has dealt with carbon dioxide historically. Because something a lot of people don't appreciate about carbon dioxide is the scale of the issue. When we look at the Clean Air Act and we look at other pollutants like SO2, for example, it was very well handled by the Clean Air Act. The Clean Air Act goes back to the legal principle that polluters should pay for their pollution. And it was implemented in the 60s and 70s. And if you take a pollutant like SO2, it was very well addressed by the sort of cap and trade ideas in the Clean Air Act. And we've done a great job mitigating SO2, but there's still a lot of work to do in that area. Folks have tried to apply the same idea to CO2. In fact, the EPA is currently making rules for regulation to regulate CO2. But if you go to the exhaust stream of a coal-fired power plant, it might be 12 to 15% CO2. The amount of SO2 is a fraction of a percent. And so putting a sulfate scrubber, an SO2 scrubber on a coal plant and charging the polluter for that amount of SO2 is a really feasible thing to do. But trying to charge for all the CO2 being emitted would require more money than that exists in the world almost. For example, we think that humans are putting something like 30 billion tons of CO2 into the atmosphere today. And we think that if we could mitigate just about 10 billion tons of CO2, that would make a substantial change in terms of getting to that 2-degree warming. When we were at the Copenhagen Climate Accords in 2009, the the idea was the developing world would need $100 a ton to not emit CO2 into the atmosphere, paid for by the developed world. Well, 10 billion times $100 is $1 trillion. So that would have the developing world paying the developed world paying the developing world $1 trillion a year not to pollute. And those are broad numbers, and I'm not even sure that's feasible, but there just isn't that much money. So creating a mechanism, a sustainable economic mechanism, aside from even getting to the technical challenges, to induce people not to pollute, not to put CO2 into the atmosphere, isn't feasible. It doesn't pencil. It's not even remotely doable. And so we have to think more broadly, if we're really serious about doing something, about how to make mitigation, large-scale mitigation of CO2 sustainable. We can't just outlaw all coal-fired power plants because the Chinese aren't going to do it, the Indians aren't going to do it, and frankly, our Congress isn't going to do it. So, and even if we did, these lights wouldn't be on. A lot of the power in California actually comes across the state border from coal-fired power plants. And when all the venture capitalists drive up and down Sand Hill Road in their Teslas that say, this is clean car, well, they're burning coal to power those cars. So where is all the carbon on Earth anyway? Well, in the atmosphere, there are about 400 million, 500 million billion tons of CO2 in Earth's atmosphere. Let me repeat that. There are 400 or 500 billion tons in Earth's atmosphere of CO2. In the whole hydrosphere, the oceans, the rivers, the lakes, there's a few thousand billion tons. In the whole biosphere, there's a few thousand billion tons of carbon. But in the lithosphere of the Earth, there's about 70 million billion tons of carbon in the form of limestone. And almost all the limestone is the fossil remains of ancient marine organisms. If you're interested in that, there's another class I've taught here called carbonate sedimentology, which is how limestone forms. So if we look at something like the White Cliffs of Dover, that's about 10 billion tons of carbon that was trapped about 100 million years ago, and it's still there. The pyramids are built out of limestone, very stable material, and it's a process like this coral up here, making something which turns into limestone. So that's historically, meaning over the history of the Earth, where all the carbon's gone. It's gone into limestone. Now, if we look at what we think about the past and what we think CO2 levels have been in the past, going from about 500 million years ago to 400, 300, 200, 100, here where the White Cliffs of Dover were formed, up to the present. Right now we're talking about CO2 just having passed 400 ppm. And it's been sort of in the 300s for most of our lives. Now it's up at Mauna Loa, we're seeing it pass 400. Well, these curves are all over the place, but they do seem to agree that CO2 has been different in the history of the Earth, and it's been validated. These are from fluid inclusions and many other very valid methods to look at it. And so if you look at life, say life in the ocean today, most of the taxonomic groups were extant, at least through the Mesozoic era, through very different levels of CO2, partial pressures of CO2. And for example, we believe it's likely that when the White Cliffs of Dover were formed, that means the organisms, the coccolithophorids, which are these plants that live in the ocean, are responsible for a lot of the carbon on Earth, a lot of the primary production on Earth. We believe CO2 is about 2,000 ppm, roughly 5 times what it was today. And some of the species, in fact, one of them, we're certain hasn't changed much since 100,000 years ago. So the way we think about carbon dioxide as a pollutant that can be regulated may not be it might not be the right way to look at it, because it's actually probably the most abundant raw material on Earth. And it's what trees are made out of, it's what coral reefs are made out of. That's the primary raw material. And if we change our philosophy a little bit about how we look at it, it might give us other solutions for our problems. So when we look at the most extensive calcium carbonate deposits, the limestone deposits on Earth, they formed, like I was saying, when CO2 was much higher than today. Of course, there weren't any polar ice caps. The world was a lot warmer. Sea level was a lot higher. Plants were going crazy because plants like CO2. You know, in Holland, they pump CO2 into the greenhouses so the tulips will grow faster. Turns out coral reefs love CO2 also because corals have plants in their tissue that are an important part of the mineralization process. So our whole view of just ticking it off as another pollutant like NO2, NO3, NO, CO, and all of that, SO2, probably isn't the right fundamental philosophical way to look at CO2. It's just another pollutant that needs regulation. So at the same time the White Cliffs of Dover were forming, there were the most extensive reefs that ever formed on the planet forming. And now this is a modern tridacnid clam, you know, the classic man-eating clam. But I show this photo to show you that the tissue is very deep color. That's because it's full of plants that are photosynthetic. Even though it's a mollusk, it's a clam. It's full of plants. And here's a similar organism called a rudistid clam. And these form massive calcium carbonate reefs all over the world, around the tropical area. So a lot of the Middle East, Irian Jaya, Mexico, a lot of these massive limestone deposits that are known are formed by these guys, which actually outcompeted modern day corals on the reefs at that time for various reasons. And we see these all over the planet. So at least in the history of Earth, when CO2 has gone up, the calcium carbonate forming organisms have flourished, as well as plants. Now here's just one experiment. This is a very well-known experimental model. It's a coccolithophorid. It's called Emiliana huxleyi. And if you ever fly to Europe in the summertime and you see these massive blooms in the Atlantic Ocean of just hundreds of miles of white, that's these guys. They have about a 12-hour life cycle. And they form these discs of calcium carbonate, and they have chloroplasts. They're photosynthesizing. And so this was an experiment published in Nature a couple years back. It's received a lot of attention. They took Emiliana huxleyi and they varied the amount of CO2 in the atmosphere over the seawater in which it was living. And then asked the question, how did that affect the calcification of these individual coccoliths, which is, if you went to the White Cliffs of Dover, it's almost 100% these guys. That's what makes up those white cliffs, the chalky white cliffs. And what they found is if you go to modern day CO2 levels and you look at the actual volume, and they looked at mass, they looked at a lot of things, and then change it to where we think Earth's going, they actually calcify more. And now we're seeing this in a whole variety of groups that were extant, that they have the genetic heritage in their genome to have lived through the Eocene thermal maximum a number of things. The reason everything's dying, not everything, is it's happening so fast right now. But the point I'm trying to make is that if we look at CO2 as a raw material as opposed to a pollutant that can only be eradicated and thrown in landfills, there aren't landfills big enough to put all the CO2, by the way, then our whole philosophy about how to mitigate it changes a lot. Some people came along and said, well, your experiment's probably invalid. There's probably something about your methodology that made these coccoliths respond in the wrong way. So the researchers said, okay, fine, let's go backward in time. And let's go check the sediments over the last couple hundred years. And in fact, going back in time, they found that we believe in the pre-industrial era, PCO2 was on the order of 270, 290. And in fact, as you go back, they get smaller. So there's a lot of work around this area. But the point is, if we open up our minds a little bit to think about how to think about this problem, we can change the way we come up with answers for it. So how big is the problem? Well, humans are putting out about 30 billion tons of CO2. About 10 of it comes from electrical power generation, mostly from coal plants. Another 6 or so comes from industrial plants, mainly cement plants, but other plants. And these are point sources. These are locations where you can actually go and trap the CO2. We can't do that with cars. Cars are just tailpipes, and we don't know how to capture all the emissions coming from cars. And so, one positive thing about electrification is even if you generated the power by burning coal, if you could capture all that CO2, transmit it out to power electric cars, you'd be taking most of the CO2 off from transportation, which would be phenomenal. So the concept, though, is we do lose the battle if we don't address this. No matter how good the Montreal Protocol is, no matter what we do with energy efficiency, we still lose the battle unless we deal with this. In fact, I was just in Washington the week before last, and one of the authors of the Montreal Protocol, who's living these short-lived pollutants, said, Brent, unless you do this, we lose the battle. So let's just, point out that coal isn't going anywhere. The coal production around the world is substantially increasing. It's not decreasing. There are laws in California and a few other places that are trying to mitigate coal. But when I look at I live in Portola Valley, when I look at my PG&E bill, it says where the emission sources are, and then it has a 21% other, which means it's out-of-state coal plants bringing power into California, and they don't want to call it out on your, it doesn't look good. If we look at the different ways that electric power, and if any of you had a chance to look at that science article, who thinks that we're going to be building nuclear power plants in California very soon? What did it call for, like 30 or 40 nuclear power plants to meet our carbon goal? In case you didn't know, the 2 nuclear power plants in the state of California aren't operating right now. San Onofre is probably never going to operate again, and if Diablo Canyon ever gets running again, it isn't going to be anytime soon. And you can be 100% certain there's no way ever another nuclear power plant is ever going to get permitted in the state of California, at least in my lifetime. But no matter what we do, we're going to be burning coal. And right now there's a rule before the EPA that says any emission for electricity for new power generation is going to have to be below 1,150 pounds per megawatt, which virtually eliminates coal. But what will happen is when they realize there won't be electricity to keep the hospital going and the guy in the respirator, the independent system operator network that's responsible for grid stability will just step in, and the regulation won't be able to be enforced. So when we look at the vast disparity between what governments think they're doing, what special interest groups think they're supporting, in the reality of the situation, it's so great, it makes you sort of wonder what we're all thinking about. But this is the scenario in the reading from California. So with energy efficiency, we're going to get that blue wedge. With electricity decarbonation, and they talk about CCS, meaning we're going to separate CO2 and inject it into the ground, which is proven to be completely unfeasible, even though governments have put billions of dollars into it over the last 7 or 8 years. It's absolutely never going to happen. Smart growth, PV roofing, biofuels, non-energy CO2, which means making cement, and electrification. We're hoping to meet our goal in California by 2050. But I think if you read the article, the authors say they don't think it's possible, even with this detailed analysis. So, you know, in my generation, we grew up thinking there was going to be a nuclear war. And we had duck and cover drills where we'd sit under the desk and things like that. But no one really had the ability to deal with nuclear war. It was so intangible. What could anyone do about it? And that's sort of how governments are dealing with climate change right now. There's a lot of measures to address climate change, but none of them pencil out, not even close. So if we look at something like cement, cement's the third largest source of anthropogenic CO2. And it's the cementing component of concrete, and concrete is the most used building material by far. It's more than 50% of all buildings. It's the most traded material other than water in the whole world. And for every ton of Portland cement you make about a ton of CO2 and put it into the atmosphere. And it really is unavoidable. The way you make it is you calcine limestone, and it just re-releases that CO2 that was trapped when it was first captured by the organisms. And we see the same thing with cement production as we see with coal production. So right now in Asia, for example, there's a lot of concrete being poured, and there's a lot of coal-fired generation being poured. And CO2 is a global, long-lived pollutant, so it doesn't matter whether you're burning it in Asia or in Northern California. We're still going to see the same global effect. Well, if we get into it in detail, why is it such a problem to just capture all the CO2, even if you could inject it into the ground? Well, if we look at what's actually being emitted, if you go to, say, an ethanol refinery, or most refineries, they're producing 95 to 100% carbon dioxide. If you go to, say, a cement plant, they're producing more concentrated, 30, 40% carbon dioxide. If you go to a coal-fired power plant, it's 10 to 15%. And if you go to a natural gas plant, it's 4 or 5% CO2. And so in the blue is depicting the quantity in the US of these different CO2 sources. And you can see most of it's coming from coal. And this is fairly true on a worldwide basis. Depicted in the green is the estimated cost of separation, which also has a proportional carbon footprint associated with just separating it. So for example, to use a conventional process to separate CO2 from coal-fired exhaust, it costs somewhere around $50 to $60 a ton, but it also uses about 30% of the power from the power plant to do that. So we call that a parasitic load, which increases the carbon intensity of a plant. So the scheme that when we went into to the Copenhagen Accords was companies were going to build scrubbers, their MEA processes, chilled ammonia, and they were going to separate all the CO2 from coal-fired exhaust. We were going to build pipelines to transport that CO2 as a liquid. And then we were going to pay oil companies to inject it into the ground. And there are billions of dollars that have been spent, and they're still being spent at the Department of Energy and foreign analogs to study this methodology. Even though we've determined that within 10 years we'd run out of reservoirs potentially. But the main issue is if you already spent $50 just separating it, you still have to build the pipeline, inject it into the ground, monitor it, get insurance, make sure it doesn't leak out and kill 1,000 people like it did in Lake Nagal in Africa, where a big bubble came out of a lake and downed a whole village of 2,500 people in about 5 minutes. And for American Electric Power, they had the first carbon sequestration test at their plant in Tennessee. And in the news is a picture of a lady at a playground with her children in the power plant in the background saying, I don't want CO2 buried in my backyard. So it's not a very feasible methodology. So going back to the idea that CO2 can be a raw material, and you can use it that way. Here's the plan, is if there are about 16 billion tons of CO2 a year, and we want to do something different with it, how about storing it in the built environment? How about storing it in all the concrete that's being poured every year? There's about 32 billion tons of concrete being poured every year around the world. And for every ton of CO2, which has a molecular weight of 44, you can make about 2 tons of calcium carbonate material. And someone's already paying for it. You don't have to come up with any new money to pay for it. So another way to look at it is we have a problem we're trying to address where there are 15 billion tons or so, 16 billion tons of CO2 being emitted in the atmosphere every year. And on a continuous, ongoing, sustainable basis, we're using about 15 billion tons of concrete, and we're actually mining about 20 billion tons of rock to put in the concrete. So concrete is about 10 or 15% Portland cement, which is that CO2 intensive binder material. And the other 80% or so of concrete is sand and pebbles and rocks and aggregate. And the main point about it is not only is this technically feasible, and it's already been demonstrated, and I'll show you, but it's economically feasible and sustainable. There's already money there. For example, when you go to fill up your car with gas, you might notice there's, I think, an 8.7% federal tax on the gasoline you pump into your car. And that money goes to the Department of Transportation in Washington, D.C. It's a lot of money. And the way they manage it is then they dole out the money to the states. So California, Caltrans, the guys in the orange vests on the side of the road, that's our Department of Transportation. Caltrans gets about $11 billion a year from that gasoline tax you pay. And what they do with that money is they improve roads and they build roads. And the way they do it is they put it out for bid. And because there are no US cement companies anymore, and the concrete producers are owned by foreign oligopolies, from Japan and Mexico and Switzerland and Germany and Ireland and France. Those contracts all go to foreign companies. So most of that money actually goes to the shareholders of foreign companies. But it's there. And we potentially have the ability to trap that CO2, turn it into building materials, and pay for it with the money we are already spending. The process I've been working on lately is a second generation process that enables us to capture flue gas and go to both cement and aggregate, as well as provide a carbon-rich fluid that we can put in concrete, and we're already commercializing this. We make this a profitable activity both through making aggregate, which can be used in road base and asphalt, which is a huge amount of material. We can also make a cement replacement and make concrete using the process. And for example, this is one of the first carbon technologies we're launching. This takes CO2, turns it into a new liquid form of carbonate. And when we add it to concrete, this is the 3-day, 7-day, and 28-day strength of the concrete. We're able to put significant amounts of CO2 into traditional concrete. Here's a control. Here's a couple of different types of mixtures. Some help the acceleration of setting. Some help freeze-thaw resistance. But the point is, they're all about the same, but if you look at 7 days, you can see that when we carbonate the concrete, it actually gets strong faster, which actually is very beneficial on the job site. So carbonation of concrete is already well known because there's CO2 in the atmosphere. And like the concrete in this building is already carbonating naturally, and it makes it stronger. But it's possible to make these building materials carbon negative. So if you take a traditional yard of concrete, it has a carbon footprint around 500 pounds of CO2 per yard. If we just replace some of the cement and the sand and the gravel, we can make the net CO2 about negative 1,100 pounds, meaning 1,100 pounds of CO2 is captured, turned into mineral, and used to make the concrete. If we also consider the concrete that wasn't formulated and add that on, it's actually a net of 1,600 pounds net negative CO2. So it's possible. There is a solution out there that is of the right size and scale to do this. The other aspect of making your own rock and aggregate, and I'll admit rock and aggregate is not as sexy as biotech or computers or MEMS. It's just rock, but it turns out it's one of the largest mass materials flows around the planet. And just for your information, in the state of California, Caltrans has divided the state into 26 venues, and 10 of them have less than a decade of aggregate for all their road projects. And that's because you really can't permit a quarry anymore. And we import a lot of our aggregate from British Columbia. It's barged down. It's all limestone, by the way. Turns out there's a worldwide aggregate shortage, believe it or not. In the Middle East, they actually ship the sand. You wouldn't think so, but there's a sand shortage in the Middle East. They bring the sand in from Turkey because it doesn't have salt in it and other things. So you're probably aware of sustainable food thoughts. The idea is you buy food that was grown locally and you're not transporting it as far. Well, multiply that times about 1,000 times for aggregate. Aggregate is very, very heavy. In the Caltrans study, they found that there's the average distance that aggregate's being moved in the state of California has gone from about 25 miles to almost 50 miles in the last 20 years. And so these are very heavy trucks which are making the roads wear out faster. If you make the aggregate and the cement, and most of the price of these materials is actually in the transportation. If you make it locally at the power plant, when you combust a ton of coal, you make 2.5 tons of carbon dioxide. And with 2.5 tons of carbon dioxide, you can make 5 tons of cement or 5 tons of aggregate. Via the methodology we use today, if you want to make 5 tons of aggregate, you have to go out to an open pit mine and mine it. If you want to make 5 tons of cement, you have to go to a limestone quarry, burn coal, and calcine it. So, you know, when we think about mining and the environmental impact of mining, we think about coal, right? Coal ripping off the tops of mountains and that kind of thing. How much coal do you think is mined every year? About 5 billion tons. So there's about 32 billion tons of rock mined every year. And it's almost all the coal mining is, most of it's shaft mining, not open pit. Most of the reasons tops are getting torn off, it has nothing to do with coal, it's about rock mining, open pit rock mining. So, has anyone ever done this before? Well, yeah, it turns out in World War II, there's a group in the Army called the Seabees that would go out and they would get the coral rubble, the sand. If you've ever dove on a coral reef, you'll notice in the back reef there's a lot of the same limestone precursor material. It's the skeletal remains of corals and clams and other calcifying organisms. And if you've ever walked on the beach in the tropics and you see where a fresh stream comes out across a white sand beach, it gets hard. That's called beach rock. That's because fresh water makes the minerals in skeletal materials unstable, and they recrystallize and cement up hard, and that's how limestone gets formed. And they actually took advantage of this and formed runways all over the Central Pacific. They're still there. I was just one in the Cook Islands a couple months ago. And the most interesting thing to me, though, was I was reviewing some of this with George Schultz, who's here at Stanford, who heads the Energy Initiative. And he said, you know what, I was there. I was a 19-year-old Marine, and I saw these runways being built. And that's just interesting because one of his jobs in life is he was the CEO of Bechtel, which is a large EPC firm which has probably poured more concrete than anybody in the whole world. So he'd both seen these formed as well as, you know, been in that position. So the concept of forming large-scale structures with limestone, basically, is already there. And this has been done significantly. In the time frame of about 2007 to 2010, I built about a $45 million carbon sequestration plant over on Monterey Bay next to the largest power plant on the West Coast, which is a 2.2 gigawatt plant. And we built a couple of lines from the two 550 megawatt cogeneration combined cycle plants over to an old decrepit refractories facility and made cement, which has been used to widen Highway 1 in Santa Cruz. If you've been down there lately, they've widened out the lanes where Highway 17 comes into Highway 1 going south. And so the process itself is something that can be done. We've now developed a second generation that's even more economical and developed. But at that plant, we looked at first going to Inner Mongolia to put a plant in, and worked with Bechtel to work out a lot of the balances. There's a lot of ways to get this going, even here in California. Typically, pollution mitigation equipment is paid for through rate base. So if I have a coal-fired power plant in Wyoming and the EPA promulgates a regulation that says I have to put my SO2 levels to a certain point, then I apply to the Public Utilities Commission for $250 million or whatever it costs to put that in place. And when that's approved, then I put that in the rate base to pay for it. So the capital costs of building these plants can actually be integrated right into the rate base of normal utilities. So it's very possible. So, you know, there's a way for large-scale sustainable mitigation of CO2 of the scale that can address most of the problem. You know, that we'll deal with the CO2 as well as criteria pollutants, but store it in aggregate and roads. These materials are also very light, so they have a high albedo and have a lot of other benefits. So, you know, I wanted to leave enough time for questions, so I was going to wrap it up, if that's all right. So I think I'll wrap it up there.
Questions? Great ones. Is there anything Brent hasn't covered?
Yeah.
So, you had that slide that showed like coal to CO2 to cement or concrete. So I was wondering, when you burn the coal, you get a certain amount of energy out. How much of that energy is then put back in to make the cement or the concrete?
Yeah, so that's a great question. So when we're talking about traditional processes, we talked about the parasitic load, which is what we'd call that. And so with the traditional processes, the parasitic load today is about 30%. And it, I guess I've seen calculations that the theoretical best would be about 18 or 19%. With the process we're using, it's a little less than 10%. So it's substantially lower. And that's one of the big advances that we've made in the last 3 or 4 years. The plant we built down in Moss Landing had varied parasitic loads depending on what raw materials were available, but they could be as high as 25 to 40% as well. So in the first generation, it really didn't provide a huge advantage over the traditional methodologies, except that if you considered the offset of the cement you weren't using, it brought it way down below that, because you know, you also were offsetting the CO2 that would have been generated by the cement formation. But now what we have with the second generation, we're even further along. And one of the issues there was, if there wasn't a price on CO2, it was difficult to make the economics work. And part of being successful would involve being economically sustainable. And even though there's not a price on CO2 in most parts of the world today, with the new generation of process, it can be economically sustainable even without a tax. So for example, a ton of cement costs about $100. A ton of aggregate can cost between $5 and $20, but it can be even $80. Most of the cost of aggregate is actually in the transportation, so how far you have to transport it. It's not the actual cost of mining the rock. And remember we were saying in that traditional process, it was about $50 a ton just to separate the CO2 before you even made anything. So it was almost impossible to make the economics work for making liquid CO2 and injecting it in the ground, or using my first generation process at Moss Landing. But with what we're doing now, we can make it economically sustainable. So even in countries where there isn't a tax or some sort of tariff for mitigating CO2, we can make it a profitable activity, which will induce people to do it.
So you're in the black, and rolling out now is just getting enough capital behind it to deploy this in as widespread a way as you can? What's the path?
Well, the second generation is just off and running, and we've just developed the first product. And actually, I can pass these around. This is from the American Concrete Institute. This is a liquid of carbon dioxide, which is just mixed with the current concrete formulations and reduces the carbon footprint of the concrete. Yeah.
So for large-scale applications of this, is there a problem with the amount of calcium you would need, or is there another material you would use in addition to calcium?
Well,
It's a lot.
yeah.
The material you're talking about.
Yeah, absolutely. So in what I'm passing around, there is no calcium. It's just a liquid. It's a liquid admixture. It's a brand new discovery, actually. One of our PhDs made it and described it first in 2012. And it's called a liquid condensed phase. It's very interesting. It turns out a lot of the carbon in water and in the ocean is not in the state we thought it was in. And it has to do with new instrumentation that allows you to observe this. So, ready-mix concrete has lots of calcium in it. So there's no shortage of calcium. But when we do make our own aggregate, our own cement, we do need either calcium or magnesium. And in seawater, there's plenty of magnesium. It's an unlimited source. Turns out, you're probably familiar with what hard water is. That water that clogs your shower. If it forms a little white deposit, that's calcium carbonate that's forming. And to put it in perspective, the ocean has about 400 ppm calcium in it. That water that clogs your shower is sort of 2,000 to 5,000 parts per million calcium. But for example, at my first generation company, we got a large DOE grant, about $47 million, to build one of these out in Wyoming at a 2.1 gigawatt unscrubbed coal plant. And so we hired Schlumberger, which is basically a drilling company. They have a whole water services unit to look around. And it turns out hard water is really easy to come by. In Wyoming, for example, they have, this is a huge number, 300 billion gallons of what's called produced water they have to get rid of every year. And they mostly inject it back into the ground. And there we had wells that were 50 to 70,000 ppm calcium. And basically anywhere you go, you can find really hard water. So I had a whole GIS team that would look at that. It's interesting, like if you go to like the state of Mississippi, anywhere where there's limestone in the subsurface, it's all over the place. But it's an excellent question because, just like when you site a cement plant, the only place you site cement plants is on a limestone quarry. So if you don't have limestone, you don't make cement there. If you're doing what we want to do, you don't do it anywhere where you don't have access to all the raw materials you need. I'm excited about this first product though because you need to understand the concrete industry is very conservative. They don't move fast. For obvious reasons, they hate it when bridges fall down. And I have that experience because I had 2 orthopedic companies that made bone cement for orthopedic surgery. And orthopedic surgeons are a lot like engineers that build structures in concrete. When they have a bad day, it's a really bad day. And so they tend to be very conservative. So as a result, they really only want to adopt incremental advances. They're not looking to change everything in one day. And the beauty of this is we get a tremendous amount of carbon into the existing concrete, and there's already 15 billion tons of it being poured every year anyway. And we're not changing their behavior. We're not adding costs on. We're not even using different specifications for them to adopt it. So, one of the themes in climate change is there's a need for speed. And if we're going to get out there quickly and start trapping CO2 and sequestering in the built environment, we need something that can get adopted into the market quickly with rapid penetration. And when you want to do that with a very conservative market, it better be a very incremental change, not a total change of the way they do everything, because they're not going to adopt it. I should say, every yard of concrete poured today, worldwide, I guarantee you, except for a few exceptions, has a material called fly ash in it, which is a substantial portion of the concrete. And they put fly ash in because it increases the strength. It also lowers the amount of Portland cement you need in the concrete, which is the most expensive component of the concrete. So the process of moving materials from coal-fired power plants to concrete ready-mix plants, which is where concrete is delivered from, is already in place. It's happening 24/7 everywhere you go around the world, moving a coal combustion product to concrete ready-mix plants for inclusion in concrete. The Bay Bridge mix design was 50% fly ash. And all that fly ash actually was brought from the Powder River Basin to California to mix in.
And fly ash has some nasty things in it, right? It's got
Right, so-
asbestos-like particles and stuff.
Yeah, fly ash is full of mercury and a whole bouquet of interesting things. But frankly, you don't want to know what they're doing with the mercury today that they're getting from mercury scrubbers. It's really, if you think of all the places to store all these pollutants, the safest place to actually put it's in the roadway. And the EPA has very strict leaching tests, which we had to perform on the minerals to show that these materials. Leslie and I were talking at lunch about there was one group that had an idea that we were going to mine hundreds of millions of tons of limestone, take it to coal-fired power plants, run the CO2 from the power plants through seawater, create carbonic acid in the seawater, then run it over the limestone to dissolve the limestone to make bicarbonate, and then dump that in the ocean to get rid of it and solve the climate problem that way. And of course, putting all those heavy metals in the ocean wouldn't, aside from the hundreds of millions of tons of limestone you'd form and all that. So there are a lot of solutions that, are all interesting ideas, but if you kind of go through them a little, they don't really pan out. Yeah.
Earlier you showed a graph that had your process versus the traditional one for the aggregates, where you had like the X's over the things and the green arrows over backwards. Yeah. I was a little confused on there. You had, I don't think I was interpreting it right, you had 1 ton of coal going to 2 tons of 2.5 tons of CO2.
Right, because you had 2 oxygens on, so the molecular weight of carbon is 12, and the molecular weight of CO2 is 44. So yeah, when you combust a ton of coal, which is primarily just carbon, you get about 2.5 tons of CO2, yeah.
Oh, the molecule, so 2.5 tons by weight?
Yeah, so by mass, if I take a ton of coal and I burn it.
And then then that turns into 5 where do you get the materials to turn into the 5 tons of the 2 separate things?
Okay, sorry about that, I kind of went through that fast. I figure you guys are all experts though. But anyway, yeah, so molecular weight of carbon is 12, molecular weight of oxygen is 16, so if you put 2 oxygens on a carbon, you get 44. If you put another oxygen on to make it a carbonate, you get, then you're up to 60. And then the molecular weight of calcium is 40. So the molecular weight of calcium carbonate is 100. It's 100.04, but anyway, it's 100. And that's a rough calculation, but if you take a ton of CO2, you add an oxygen and a calcium, the mass is 100.
This ties in with the things you were asking earlier about where you get the calcium. Is the cost of moving the calcium substantially lower than the cost of moving the other things? Because you said the main cost factor is moving stuff around. So. Right.
Yeah. So the main source of calcium is through water. And I meant to say a little more. So one issue around the U.S. today is what to do with all the produced water. Sometimes it's wastewater. Sometimes it's coming from oil drilling. Right now, there's a ridiculous amount of water coming from a process called fracking, where they pressurize it and bust apart the rocks, and then they have to inject it down and bring it back up, and you have this huge environmental problem that doesn't look like it's going away anytime soon. The price of gas is very low. You know, the government doesn't want to see coal, so there's more gas. And you're going to see more and more fracking and more. I mean, it's a terrible problem, actually. You know, I just mentioned, I forgot to mention in the lecture, you know, one of the things we've learned through this process is we don't have a very good idea how much CO2 humans are really putting into the atmosphere. For example, when you bring water up from the ground, you bring anything up from the subsurface, you bring it from pressure to almost no pressure. So just to give you some numbers, if you take 100 gallons of water at 1 atmosphere pressure, 5 degrees Celsius, you can get about 1/3 of a pound of CO2 into that from the solubility of CO2. If you put it under just 10 bars, which is about 150 psi, which is about 270-foot depth in the subsurface, which is not very deep, you can put 15 pounds. So all over the state of California, where we're bringing water up from depth, it's almost always saturated with CO2 because there's no photosynthesis. It's all respiration down there. We're off-gassing ridiculous amounts of CO2. But the water quality boards don't really take it into account. You know, everyone knows when water comes up, it effervesces. Well, the reason it looks like your soda bottle is that's the same thing that's happening. You're uncorking it. And, you know, the amount of CO2 we're bringing up from fracking, from oil drilling, just from potable water, you know, is probably on the order of one of those wedges. And the water board doesn't even want to know about it because it's so scary to even think about it. And there's probably other significant outlets of CO2 that we don't even account for. And you know, a lot of the problem is a lot of the accounting's done by non-scientists. A lot of the modelers are just grasping numbers which are not very solid numbers and putting them into models. And this is done at a very high level. You know, and part of it is, you know, when they put together groups like the Intergovernmental Panel on Climate Change, you know, they'll choose a physicist and an economist. And by the time they get into a model, the fundamental grounding in the science isn't there. And it's really remarkable how unreliable the numbers, like in the paper you read, really are, in terms of really getting our arms around this and understanding it.
So the fracking and the bringing up the water and drilling is also releasing a lot of methane, right? But that's nothing that you're addressing in this particular.
No, and that's true. So methane's like a 22 times more powerful greenhouse gas than CO2. And yeah, there's a lot of methane, CO2, other things being brought up with all that water, and it's not being monitored. State of California is interesting. We're the only state in the country where you don't have to report how much water you pumped out of your well every year, because we have a very strong agricultural lobby. And you know, so the California Water Board cannot go out and, you know, make a registry of how much water is being pumped out of the ground every year. There's no way for them to get that information. And, you know, that's California. You can imagine what it's like in the rest of the world in terms of understanding that. And so our basic understandings aren't very good. And you know, most of the effort's going on documenting how bad it is. You know, there's very little effort going into how to mitigate it and solve the problems. You know, and the effort that's going to document it, you know, doesn't really pass a rigorous review of the numbers going into it.
You mentioned something pretty ironic sounding, if I caught it right at the beginning of your lecture, and that was that coral reefs thrive with higher CO2 concentrations, but that things are moving so quickly that they're in fact dying? Did I get that right?
Yeah, and I think we're in the middle of just beginning to understand what's happening. Steve Palumbi, who's the director of Stanford Hopkins Marine Station down in Monterey, is just doing some fascinating work right now. He's working down in Indonesia, and his students are looking at coral reefs that are basically dying. They're bleaching their corals. And it's probably due to high surface temperatures. You know, and that typically happens when the surface water temperatures get so high. Hermatypic or reef-building corals have these symbiotic dinoflagellates in their tissue, zooxanthellae, that they're symbiotic with. They photosynthesize, they take in waste products from the animal, they return carbohydrates, and everybody's happy. But when the temperature gets really high, they'll jettison their zooxanthellae, and they look white because their tissue is clear. You just see the white skeleton underneath. And then they often die after that. But there are these subpopulations where the water's very hot. You know, like, I mean, I don't know, something like 38 degrees centigrade hot, 40 degrees centigrade. And they're thriving. Whereas the same species 100 yards over there isn't. And so they're beginning to ask some really interesting questions. And one thing they've done is genotype these corals. And they're finding that the ones that are thriving have 4 or 5 specific genes that the other ones don't have. And these are in taxonomic groups that were extant back in the Cretaceous. And they lived through the Eocene thermal maximum 40 million years ago. So, you know, it's likely that the genetic heritage, you know, the variation to deal with these changes exists in the current genome. But the chances that it'd be able to respond in our lifetime or the rate at which, you know, it's increasing are like 0. You know, so, you know, I'm not saying let's pump a lot of CO2 to the atmosphere. I'm not saying that at all. I'm just saying we're learning a lot more about how to think about CO2. Because in general, it's like investing in the stock market. You know, in general, they say if you're in the stock market, you're going to make money over time, but it goes down real fast and up and all that. In general, over the history of life, increased CO2 appears to have improved reef building, you know, improved the marine phytoplankton that are calcifiers, and had these kind of effects. I mean, but if you think about drastic measures to save a reef, like take the Mesoamerican reef off Belize, there are hundreds of miles, literally, of dead elkhorn coral, and it's really sad. But if you're swimming along every 100 yards or so, you'll find one that's really happy. And you think, well, what was different about this one? And you know, if someone was going to take a drastic measure, you'd go genotype that, or you would clone it, and you'd redistribute it, you know, to try and reestablish those reefs before they're taken over by algae, and and it's complicated. You know, there's overfishing, there's agricultural runoff. I mean, there's a whole bunch of things. There's temperature, it's acidification.
I'm hearing some consistency with, remember Terry Root's lecture at the very beginning of the quarter, where, you know, and plant and animal populations can respond to changes in conditions, but it's rapid changes, all in the same direction, is
right.
What's a problem. And I think you're saying, given a little slower, you know, evolution of what's going on, that coral reefs could respond, but as it is, a few are pretty lucky, but to have that be widespread, it can't happen in time.
We might just say, might be that coral reefs are over. You know, I did my dissertation on corals and how they form their skeletons, and compared to the way they were in the 80s, it's dramatic, although there are a few places where they're still around. But if they do continue to survive, we're going to see a real change in what species and genera actually compose the reef, and that's going to change the whole shape of the reef, you know, and the wave-resistant structures and all that kind of thing. My point about bringing it up is just, you know, in the natural world, CO2 is the biggest raw material. It's not a pollutant. You know, and if we're biomimetic and we're going to learn from that, we're going to see it as a raw material and take advantage of it. You know, the largest structure on the planet is the Great Barrier Reef. And it's all calcium carbonate formed by calcifying organisms. You know, it's been there for a while.
Any last questions? We've got a couple minutes more. This is critically important. Thank you for sharing it with the class. I mean, this gives me one more ray of hope out there, what you're doing. So thanks a lot.
Scrubber, an SO2 scrubber on a coal plant, and charging the polluter for that amount of SO2 is a really feasible thing to do. But trying to charge for all the CO2 being emitted would require more money than that exists in the world almost. For example, we think that humans are putting something like 30 billion tons of CO2 into the atmosphere today. And we think that if we could mitigate just about 10 billion tons of CO2, that would make a substantial change in terms of getting to that 2-degree warming. You know, when we were at the Copenhagen Climate Accords in 2009, the idea was the developing world would need $100 a ton to not emit CO2 into the atmosphere, paid for by the developed world. Well, 10 billion times $100 is $1 trillion. So that would have the developing world paying the developed world paying the developing world $1 trillion a year not to pollute. And those are broad numbers, and I'm not even sure that's feasible, but there just isn't that much money. So creating a mechanism, a sustainable economic mechanism, aside from even getting to the technical challenges, to induce I'm going to be teaching this spring my most common course, which is over in Earth Sciences, but I think it's cross-listed in engineering still and in the School of Medicine, which is biomineralization, which is how organisms manipulate crystal formation. So if you're really interested in a lot of detail, that would be a course to look at. But what I want to talk about today is what a lot of people think is the only definitive way to address climate change. You guys are probably all aware that recently we've learned that some of the non-CO2 gases can be mitigated, like the HFCs and other gases, and China just agreed to join the Montreal Protocol, which is on these short-lived pollutants. And we've learned that you know, that's going to be a huge benefit to climate change by controlling these short-lived pollutants. And you're not aware of it, but over your lifetimes, you know, refrigerators and air conditioners have changed the types of chemicals that are used in there and getting into the atmosphere, which are very powerful greenhouse gases. And the Montreal Protocol has been one of the most successful legislations. And that's going to certainly help things out a lot, but we still lose the whole climate battle unless we do something about CO2. And you know, the reality is that coal is going to be the principal fuel for electricity for our lifetimes. Even if we tried to go to 100% renewable as fast as we possibly could, we'd still have to burn coal for at least 50 years to get there, and that's the harsh reality of the situation. And with half of the population of India being under the age of 14, and what's happening in China and coal reserves, for our lifetime, coal will be the main thing powering electric cars. And unless we address those sorts of emissions in a real definitive way, we lose. We exceed the 2 degrees, and other things begin to happen. So the one single most important thing if we're really serious about doing something about climate change, is to mitigate CO2 emissions primarily from electrical power generation. And so I'm going to talk a people not to pollute, not to put CO2 into the atmosphere isn't feasible. It doesn't pencil. It's not even remotely doable. And so we have to think more broadly, if we're really serious about doing something, about how to make mitigation, large-scale mitigation of CO2 sustainable. We can't just outlaw all coal-fired power plants because the Chinese aren't going to do it, the Indians aren't going to do it, and frankly, our Congress isn't going to do it. So, and even if we did, these lights wouldn't be on. A lot of the power in California actually comes across the state border from coal-fired power plants. And when all the venture capitalists drive up and down Sand Hill Road in their Teslas that say, this is clean car, well, they're burning coal to power those cars. So where is all the carbon on Earth anyway? Well, in the atmosphere, there are about 400 million, 500 million billion tons of CO2 in Earth's atmosphere. Let me repeat that. There are 400 or 500 billion tons in Earth's atmosphere of CO2. In the whole hydrosphere, the oceans, the rivers, the lakes, there's a few thousand. A little bit about how nature has dealt with carbon dioxide historically. Because something a lot of people don't appreciate about carbon dioxide is the scale of the issue. When we look at the Clean Air Act and we look at other pollutants like SO2, for example, it was very well handled by the Clean Air Act. The Clean Air Act goes back to the legal principle that polluters should pay for their pollution. And it was implemented in the 60s and 70s. And if you take a pollutant like SO2, it was very well addressed by the sort of cap and trade ideas in the Clean Air Act. And we've done a great job mitigating SO2, but there's still a lot of work to do in that area. Folks have tried to apply the same idea to CO2. In fact, the EPA is currently making rules for regulation to regulate CO2. But if you go to the exhaust stream of a coal-fired power plant, it might be 12 to 15% CO2. The amount of SO2 is a fraction of a percent. And so putting a sulfate